All right, what is up, everyone? Today we're going to go back to probability. We already did geometric probability. This will be very similar, particularly this lesson. We're just going to get into some different terminology and some different forms of probability in the upcoming lessons. We're only going to have 3 lessons in this chapter. We're going to have 1 quiz. It will be all due on that Wednesday of next week. So let's go ahead and get started. So introduction to probability. You should know some of this stuff from when we did probability the first time. Well, probability is how likely something is going to happen. When we did geometric probability, it was like, what's the probability of hitting a target, like a small circle inside a big square, where we calculated the area of that circle and that square. Well, the good thing is we don't have to calculate any areas for people that were worried about that as we started. Instead, we're going to talk about things like coins, dice, and cards. Those are going to be our major things for kind of these probabilities and just given numbers. So we won't be calculating stuff to start off with. We're going to use numbers that are already given to us. So many events can't be predicted with total certainty. When I flip a coin, you're not 100% certain it's going to be heads or tails. If it was, betting would be pretty easy on that kind of stuff. The best way we can say this is, how likely is this going to happen? That is probability. How likely is it that I'm going to flip a head? Well, that's 1/2. You have heads and you have tails. So when you toss a coin, there are 2 possible outcomes. It's either going to be heads or tails. Now, when you list both possibilities or all the possibilities, this is known as something called sample space. Sample space is a list of all possible outcomes. So if I was rolling a 6-sided die, we would have a possibility of getting a 1, 2, 3, 4, 5, and 6. You list all those numbers out. So your sample space is all the possible things that you could possibly get out of that particular situation. We would say the probability of getting heads. Now, what I want to notice is this little notation here. See this P head thing? When you're using probability, it's not always advantageous to write out an entire sentence every single time, like the probability of getting a head, because you might end up writing it 6 times. So instead, what we do is we put a little P out front, and in those parentheses, we say what probability we're looking for. So with P parenthesis head, that just means what the probability of getting a head. Now, these are very specific to given problems. Head might be a head on a person. So we get very generic with these, and you can kind of choose what goes in there. You could say probability of getting an H. That would be fine too. So if I just got rid of this EAD, and we're talking about this problem, heads and tails, I could go probability of H happening, and we're all going to know it's a head. So they're very dependent on the problem. They're not full sentences, and you'll see when I'm using these that I'm going to use little short notation for these different probabilities. So what would we say the probability of getting a heads is? Well, we have a 50-50 shot of getting it. It's either going to be heads or it's going to be tails on one toss. So our probability is going to be 50%, most of us will say. Well, another way to put 50% is we can say 1/2. The other way we could write that is 0.5. You'll find that I traditionally write it as just a fraction, and I just keep it as a fraction. You could turn it into decimal, but you'll see on my answer key, most of these will result in a fraction. So although 50% is right, 1/2 is right, 0.5 is correct. For me personally, I usually stick with fractions. They're easier to use, and you know I do like myself some fractions. So pick any one of those 3. Just make sure you recognize that my answer key will be in fraction form. And all 3 of these mean the exact same thing. And why I'm going to point out this fraction too is that's actually how we calculate probability. If we look at that 1 on top, that's my 1 success per kind of 2 possibilities. 1 head per 2 possibilities, heads or tails. And that gets us back into what is simple probability. Simple probability is the probability of one event happening. Now, it's just one event, so you flip one coin. You don't go, I'm going to flip it, I'm going to flip it again, I'm going to flip it again. It's just one event happening. So flipping a coin is an example of a simple probability. As it is one event, you flip a coin. The probability is calculated by dividing the number of outcomes over the number of possible outcomes. Probability can be given as a fraction, decimal, and percent, which I just talked about. So probability of an event, the number of ways it can happen. So when we talk about that number of ways it can happen, there's only one possible way to be successful, and that's to get ahead. And the total possible outcomes was heads, and you could have got a tail. I guess I should say head and tail. Actually, it should be head and tails. All right. So we have 2. So it'd be 1 over 2. That's where we came up with that 1 over 2 from. So kind of like success over what are your possible outcomes. All right, the next thing we're going to have is what is the probability of rolling a 4 or a 5 when rolling a single die? Now, notice we have 2 successes here. We can either roll a 4 or we can roll a 5. So as I said with a die, if I'm going to do my sample space, we would have to do all of our possible outcomes. So we'd have a 1, we could roll a 2, we could roll a 3, we could roll a 4, we'll get there, we could roll a 5. There's 5 of them there, I'm guaranteeing it, and we're going to have 6. Now you could shortcut a die, you could just go 1, 2, 3, 4 and put the actual numbers down. This is called your sample space. One die can result, that's simple space, it's the sample space. One die can result in any one of these 6 outcomes. Now to be successful, we're going to roll a 4 or 5. So when I'm doing that probability shortcut, I'm going to put what's the probability of rolling a 4 or a 5. Note, I don't have to put rolling because it's part of the problem. We're just going to say probability of a 4 or a 5. Now, to be successful, there are 2 possibilities. Either I roll a 4 or a 5. So we have 2 on top. There are 2 ways that this can be successful. Out of how many ways could we possibly roll? We could roll 1, 2, 3, 4, 5, or 6. So we have 6 possibilities. So our end probability is going to be 1 out of 3. Now, just remember with probabilities, there's something called a law of big numbers. We're not going to get too much into it. I just want to specify 1/3 doesn't mean in 3 rolls I'm guaranteed to get a 4 or 5. That is not how probability works. How probability works is, say I roll 1,000. If I roll 1,000 dice back to back to back, you're more than likely going to have about 1/3 of those being a successful 4 or 5. So the larger you do this, the more likely you are to get that 1/3. The smaller sample size, if I just roll 3 die, there's a good chance I'm not going to roll a 4 or a 5. It's just not enough things. So we have a law of big numbers that the more you do, the more likely you're going to fall into that 1/3 camp, but it's not guaranteed. All right, moving on. Find the probability of observing a sum of 5 when a pair of dice is rolled. I also put a little question on there. Why is this considered a simple probability problem if there are 2 die? Well, we can think of this as being a compound event or a simple event. We're going to think of it as simple because I'm just rolling 2 die at the exact same time. There's one outcome happening at the exact same time. If we think of this as me rolling 1 die and then rolling another die, then we'll get to a compound event, although it'll be very similar in calculating. So we're going to treat this as a simple probability because I'm rolling both at the exact same time. I'm not rolling a 2 and then seeing what happens and then rolling something after. It's at the exact same time. That's why I'm going to lump it into that simple probability. Now it says find the probability of observing a sum of 5. Well, our sample space is right here. I'm not going to make you draw out all those die. We're going to notice that we have a 6 by 6, so we actually have 36 possibilities of rolling these. Now, we're trying to look for the ones where the sum equals 5. Well, sum equals 5 when we have 4 plus 1, 3 plus 2, 3 plus 2, and 4 plus 1. It's kind of nice how if you had a list like this, you'd see they have kind of an angle effect like that. So there are 4 places where I'll get a sum of 5. So when I'm looking for a probability, I'm just going to put sum 5. We have 4 success out of 36 different possible outcomes, which I can simplify down to 1 over 9. It is kind of cool that this equals 36. And we're actually going to talk about that a little bit later. But basically, it has to do with you have 6 outcomes on the first die, 6 outcomes of the second die. So 6 times 6 equals 36. Let's do one more thing. I'm guessing we can't solve this one because this isn't an example. What if we roll one die and then we roll one again? Well, I already said that that would no longer be considered a simple probability. Although we could treat it as simple, it is not considered a simple probability because I'm rolling one and then another die. So it's not just one event happening. I'm rolling a die, taking a break, rolling another die. That's 2 events I have to account for. So that's going to lead us into something called compound probability. Compound probability is the probability of 2 or more independent events. Independent is the key word there, and we're going to get to that in a second. 2 or more independent events, both happening. So when I roll one die and then another die, I roll another die, I roll another die, those are all called compound probabilities, and we can keep adding or multiplying those onto each other. So the term independent event, that means that the outcome of one event does not affect the outcome of the other event. Well, think about die or dice. If I roll one die and then I roll another one, that first die has no effect on the other die. They're independent of each other. They do not have effect on each other. Let's think of something that's not an independent event real quick. So let's think about I have a bag of quarters. Say I have 20 quarters in a bag. Let's change that. Let's say I have 10 quarters and 10 dimes in a bag. Let's say I pull out a quarter. Or what's the probability of me pulling out a quarter? Well, once I pull that quarter out, now let's say I change that up and say, what's now the probability of pulling out a dime? Well, the bag size has changed. So when I pull out that first quarter, it changes the sum that's in the bag. So when I pull out the dime, it has been affected by that quarter being pulled out. That is known as being dependent. It's dependent on what happened in the first circumstance. Usually you'll see the problems that are like without putting it back in, or something's changing every single time you do a particular action. That's when you get dependent. And we'll talk about that a little bit further down. But just know independent means the second event and the third event and the fourth event and the fifth event have no bearing on each other. They're in this little vacuum. When I roll a die, it doesn't affect the next die. If I roll a 1, that 1 doesn't disappear on that die and I can't roll it again. That is why it's independent. You must confirm that something's independent in order to use this equation. Well, the equation is you just multiply the 2 events. So you'd multiply, so the probability of getting A and B, so in other words, me rolling a 1 and then a 2 would be the probability of rolling a 1, multiply the probability of rolling a 2. So let's see that in practice. So find the probability of rolling 5 twice in a row. We know this is independent because when you roll one die, it doesn't affect the next die. So find the probability of rolling a 5 twice. So we know it's independent. So the probability of rolling a 5 and then another 5 is going to equal the probability of rolling a 5 times the probability of rolling a 5. Well, the probability of rolling a 5 on one die is 1 out of 6. The probability of rolling a 5 again would be 1 out of 6. So my first die I have a 1 in 6 chance of rolling a 5. On my second die I have 1 in 6 chance of rolling that 5 as well. So we multiply that. Remember, with multiplication we multiply the tops and the bottoms. 1 times 1 is 1 over 36. We have a 1 in 36 chance of rolling 2 5s in a row. Well, remember, I talked about just before that you can possibly treat compound events as independent a little bit. So let's think about this. We're rolling 2 5s in a row. It's kind of like rolling 2 dies as 5s. Well, if I go back to that sample space we had over here, we're going to notice there's only one chance out of 36 of rolling a 5 and a 5. So that's what our compound probability also confirmed, that if you roll 2 die, there's only one opportunity to be successful, and that is if you roll a 5 and a 5, and you have 35 ones where you fail. Moving on, example 5. A couple has just given birth to a baby girl. What is the probability that their next 2 children will also be girls? Well, this problem inherently is there to kind of confuse you, because you're thinking you're finding 3 probabilities when you're really only finding 2. So let's start that off. So it says a couple has just given birth to a baby girl. Does that have any impact on their next 2 children? And the correct answer is no, it doesn't. They already had the baby girl. It's no longer included in our probability. So what we're actually looking for is what is the probability of their next 2 children being girls? And we're going to go with the fact that having a girl is equally as likely as having a boy. So all we're trying to do is find the probability of having a girl and then another girl. Well, the probability of having a girl times the probability of having another girl is going to give us our probability. And the probability of having a girl is 1/2. The probability of having another girl, 1/2. Multiply those 2 together and you have a 1 in 4 chance of having 2 girls afterwards. And we can actually see that if I drew the sample space. Our sample space is, you could either have 2 girls, you could have a girl and then a girl, or maybe the first baby's a girl, the second one's a boy. Maybe the first one's a boy and the second one's a girl, and then we have a boy. Well, that's 1 out of 4. So that this probability works out with even treating it as a single event. All right, so I put that on there because sometimes drawing a sample space can be really easy and can really help you if you get stuck in a jam, particularly if you're talking about coins and things that are 50-50. I only had to draw 4 things and no one was successful, 1 out of 4. That's my probability. All right, example 6 says, a bag contains 3 marbles, 2 green marbles, and 4 blue marbles. 2 marbles are drawn randomly from the bag and not replaced. I'm going to stop right there. Not replaced. So 2 marbles are drawn randomly for bag and not replaced. Find the probability both marbles are blue. Now, we can't solve that one today. This is not independent. This is not independent because I'm going to draw 1 marble and not replace it. That means my second marble is dependent on what I pulled on the first one. So let's say on my very first marble I pull out a red marble. For the second one, I only have 2 red marbles in that bag now. If that first one was a blue marble, I no longer have 4 marbles in the bag for the second one. So this is not independent. It's dependent, and the word I'm looking for is not replaced. Not replaced almost always signifies that this is not going to be independent. But fear not, we will cover this tomorrow. It's not really that much more different, but we're going to worry about that tomorrow. Because the first thing I really want to talk about is complements. Complements are all outcomes in which the event does not occur. So if I asked you what's the probability of getting 2 5s, the complement would be the probability of not getting 2 5s. And there are many times where using the complement is actually easier to find our probability in event. And in fact, I have this word underlined. Usually if it says at least, it usually means we're going to use the complement. It's going to be easier to find. So let's talk about the complement really quick. So let's say PA stands for the probability of something happening. This is my probability I'm looking for. The complement is going to be listed as P prime A. That is going to be our complement. So if we have probability A of something happening, probability prime would be it not happening. And the important part with a complement is the probability of something happening plus the probability of something not happening has to equal 1 or 100%. Well, that makes sense because it's covering all your bases. Probability of something happening versus it not happening, you have a 100% chance of something either happening or not happening. So it's going to equal 1 or 100%. Let's go ahead and use that in practice. So it says, what is the probability of rolling 2 dice and getting at least 1 5? So let's say, okay, what's the probability of getting, let's go ahead and say at least, actually, let's do this. Let's say we have probability of A. Probability of A is going to stand for at least 1 5. And then when I do the complement, let's go P prime A. It kind of doesn't make sense to put a full sentence in there, so I'm just going to let it A stand for that. P prime A would be, well, the probability of getting at least 1 5, its counter is going to be getting no 5s. Because at least means I can have 1 or I can have 2. The complement of that would be not getting any 5s whatsoever. Let's go ahead and find the probability of not getting any 5s. So the probability of not getting any 5s is going to be, what is the probability? So we're rolling 2 dice and we're not getting any 5s. So the probability of not getting any 5s on 2 die would be the probability of not 5 on the first die times the probability of not getting a 5 on the next die. Probability of not getting a 5, well, there's 5 numbers that aren't 5s out of 6. Times, how about not getting a 5 on the second die? Well, that's also 5 out of 6. This is now going to equal 25 out of 36. And what I want to note, that's the possibility of not getting any 5s. But remember, this is our complement. To figure out our P of A, that is at least 1 5, what we're going to do is we're going to say, okay, that's going to be 1 minus that 25 out of 36, which would be 36 over 36 minus 25 out of 36, which equals 11 out of 36. So the possibility of not getting any 5s is 25 out of 26. That means 11 out of 36 times you're getting at least 1 5. And once again, your keyword is at least. All right, that's all we're covering today. I think the most complicated part is probably this complement. It does get a little tricky. Your key is look for that at least thing. And sometimes even when you get one of these problems, you can always draw out the sample space and solve it. All right, guys, I will see you with probability number 2.